So how do we recover these representations? How do we derive these representations from large quantities of unlabeled data? In a moment, I'm going to describe the mechanics of the Brown clustering algorithm, but firstly I want to talk about the intuition which underlies this algorithm. The intuition is that if we have a large amount of unlabeled data, we can leverage the fact that similar words tend to appear in similar contexts. Or a little more precisely, similar words have similar distributions of words to their immediate left and right. So, for example, if I take the word the and the word a, these are both they're similar words, they're both determiners. I can look at the frequency of different words to the immediate left and right. So I might find that prepositions like in and of are frequently seen to the left of the word there, that nouns like dog or park or share are frequently seen to the right. And so you can, given a large quantity of unlabeled data, you can basically look at the distribution of words to the immediate left of the word and the distribution of words to the immediate right. And I can do a similar thing for the word a. And because these two words are similar, I'm going to see a very similar distribution, or at least a somewhat similar distribution, where again I see the most frequent words being nouns like dog, park, or share to the right, and prepositions like in and of to the left. If I take another example, if I take Monday versus Tuesday, if I look at the frequent words to the left, they're going to be things like last, or on Monday, last Monday, various things here. And again, we're going to see these words like last or on frequently in this context. And similarly, there'll be a set of words which tend to appear after days of the week, and we'll see a similar right context for both Monday and Tuesday because they are both days of the week. So that's the basic intuition. And the Brown clustering method is one clustering algorithm. There are actually several possible algorithms. We're going to focus on this one. But all of these different ways of deriving these word clusters basically leverage this intuition that similar words tend to have similar distributions of words to the left and right. So now let's look at the formulation underlying the Brown algorithm. So we'll use script v to refer to the set of all words seen in the corpus, i.e. this is going to be our vocabulary, and we'll assume that the corpus consists of a sequence of words W1 through W capital T. For convenience, I'll assume that we don't have individual sentences, we just have one very long sequence of words. Think of this as the entire corpus concatenated. It's a minor detail whether we split this into sentences or not. And the output of the Brown clustering model for now is going to be a clustering. A clustering is a function C that maps the vocabulary to the set 1 through k. So every word in the vocabulary is going to be assigned an integer. So say k equals 1,000. We have 1,000 clusters. We might assign the word the to 1, a to 1, and then maybe Monday to 2, said to 3, and so on. So this function is going to map each word to an integer between 1 and 1,000, say, basically defining a mapping from words into the underlying classes. So in the Brown model, there are basically two types of parameters, and they look very similar to the types of parameters we would see in a bigram HMM. So firstly, we have emission parameters. So we might, for example, have e of the given 1, which intuitively is the probability of cluster 1 emitting the word the. Okay, so each cluster from 1 to k is going to have a distribution over the different words in the vocabulary. The second type of parameter looks very much like the kind of transition parameter we saw in HMMs. So for example, Q of 3 given 1 would be the probability of class 3 following class 1. So a Brown clustering model is going to consist of a function C that maps the vocabulary V to the set 1 through K together with these parameters, these E and these Q parameters. It's really very similar to an HMM. The main difference is that this function C is deterministic, that each word gets mapped to a single state. We're not going to allow any ambiguity where different words, or rather the same word, can belong to different states in the HMM. Now, given settings for these parameters E and Q, and given a definition of this function C, we can write down the probability of our corpus as follows. It's going to be a product of terms, I equals 1 to n, and we're basically going to have a bigram model, wi given wi minus 1. That's what this term here is. But to calculate this, we calculate this in a rather different way from what we've seen before. So there are two terms. Firstly, I have Q of C of wi given C of wi minus 1. That intuitively is the probability, given that the previous cluster was C of wi minus 1, of choosing the next cluster as CWI. And then I have E of wi given C of wi minus C of wi, sorry. That's what we have here. So you can think about this as follows. Say the previous word is the, say this is wi minus 1, and I want to calculate the probability of the next word being dog. And let's say for the sake of argument that C of the is equal to 1 and C of dog is equal to 50. So the falls into the first cluster and dog falls into the 50th cluster. Then, in some sense, what I'm doing here is I'm first mapping the word the to cluster 1, and then conditioned on that, I'm mapping to class 50 as the next one, and then I'm generating the word dog from this cluster 50. And the result is we have P of dog given there is equal to E of dog given 50 times Q of 50 given 1. So that's the basic model. The thing to bear in mind, though, is that all this machinery is really there so we can derive this clustering. So we'll see that in learning this model, we're actually going to have a method that takes a corpus as input and chooses parameters E and Q and a clustering C. But the clustering is really what we're looking for as the output of this model. We want a division of words in the vocabulary into a set of clusters such that similar words appear in the same cluster. And a little later we'll talk about how actually to optimize this, how to choose values for E, Q, and C that attempt to maximize this function. Let me give one more example of how this model works on a slightly more complicated example. So here I have the full distribution, the definition I showed you on the previous slide. And now let's assume that our vocabulary V just consists of the words there, dog, cat, and saw, or at least it has those 4 words. It might have many others. And so C of there is going to be 1, C of dog is equal to C of cat is equal to 2, and C of saw is equal to 3. That's reflecting the fact that this word appears in cluster 1, these two are in cluster 2, and this word is in cluster 3. Let's assume we have these omission probabilities. So E of the given 1 is 1, E of cat given 2 is equal to E of dog given 2 is 0.5, E of saw given 3 is 1. And let's assume we have some transition probabilities. Let's now see how we can calculate the probability of the dog saw the cat. Well, the first thing we do is we notice that each of these words falls into a cluster. So the falls into cluster 1, dog into 2, saw into 3, the into 1, cat into 2. And we can now write down the precise form of this equation for this particular example. So firstly, I'm going to have some Q terms corresponding to basically a Markov sequence under these 5 words. So I have Q of 1 given 0. I'm assuming that the class for the sort of the star word, the start of the sentence, is equal to 0. I have Q of 2 given 1 times Q of 3 given 2 times Q of 1 given 3 times Q of 2 given 1. Looks very much like a standard HMM. And then I have E of the given 1 times E of dog given 2 times E of saw given 3, and so on and so on. One omission term for each of these words. So again, very similar to the calculations we see for HMMs. The only wrinkle here really is that we have this function C that maps a word to a deterministic choice of underlying state. And so to calculate this probability, we'll first look up for each word, which cluster it falls into, and then calculate the probability of this sentence as the product of Q and E terms.